All right, we are going to continue our discussion of the non-homogeneous differential equations that are in the form of a y double prime plus by prime plus cy equals g of t. And again, just like before, our solution is going to be in the form of, or a general solution is going to have the form of the complementary solution added to the particular solution. So very similar to when we did the method of undetermined coefficients. This time we're going to look at one called the variation of parameters. So we're going to start the same way. First thing, we're going to look for a complementary solution. That's where we list our characteristic equation. We find those roots, whether they be real distinct roots or repeated roots or complex roots, and we write our complementary solution. Well, then what we're going to do is use another method to find a particular solution. The last section that we did, our particular solution, we found using the method of undetermined coefficients. And that method is super helpful if you have a very specific g of t function. Another method that we're going to look at today is called the variation of parameters. And it has some good and bad things that go with the variation of parameters. So the good thing, it can be used in way more cases than the method of undetermined coefficients. But the bad, you have to find a complementary solution this time. Whereas our method of undetermined coefficients, we didn't have to find a complementary solution. It did help, especially if our complementary solution happened to have one of the solutions we guessed at. The next thing that may be a con is that there's a lot of integration work that is required for this particular method. So it's always going to be possible to get a formula for the particular solution, but sometimes that integration work becomes too tricky and we can't actually solve for it. So that would be the next con. So let's walk through the method of the variation of parameters. I am going to walk you through a few steps before I show you the problem, just because I think it helps. Okay. So the method of variation of parameters, we're going to start with our complementary solution being that c1 times y1 plus c2 times y2, the linear combination of those terms. And the key to that is that y1 or y sub 1 of t and y sub 2 of t must form a fundamental set of solutions. Well, do you remember what that means? Do you remember that it means if we're going to form a fundamental set that the Wronskian of those two functions, so that would be y1 and y2, and then their derivatives, y prime of 1 and y prime of 2, would need to be not equal to 0. So we would get y1 times the derivative of y2 minus y2 times the derivative of y1, and that result can't be 0. So if they're going to form a fundamental set, that's going to be the key to this. And then what we're going to do is we're going to take a pair of functions. We're going to take some function u sub 1 and some function u sub 2. And we're going to write our particular solution to make this new function u sub 1 and u sub 2 be my coefficient to y sub 1 and then the coefficient for y sub 2. And we're going to make sure that we start with our differential equation of y double prime plus p of t, y prime plus q of t, y equals g of t. You'll notice here that we don't have a coefficient, or our leading coefficient is 1. We have a coefficient. The leading coefficient is 1. Okay, so if we assume that it is in fact a fundamental set, then the particular solution, if I go to solve for that particular solution, we know that this particular solution can be written in this form. It's this form here. This says y, the particular solution would be the opposite of y1 times the integral of y2 times g of t, some function g of t. That's going to be that non-homogeneous part, that function that the differential equation equals, divided by the Wronskian. And you can see then maybe where that integration can get a little bit tricky. And then we're going to add that to y sub 2 times the integral of y sub 1 times that non-homogeneous part divided by the Wronskian again and integrate that. So that is how we do the variation of parameters. This is the method called variation of parameters. So on the top of this next page, I have put that formula there so you can see it. And yes, obviously I would write this down on your note card for when you go to take your test. So let's look at how this works. The first thing that we're going to do here is we are going to find our complementary solution. So we're going to ignore the non-homogeneous part, and my characteristic equation here would be r squared minus 2r plus 1, and we're going to solve that to equal 0. Factoring that, I get r minus 1 squared, which means r equals 1 is a repeated root. And with a repeated root, remember my complementary solution would be c1 e to the 1t plus c2 t e to the 1t, and we need that extra t for that degree of freedom, for that repeated root. Okay, so the next thing that I'm going to do is I'm going to work to find my particular solution. So to do that, I think it's easiest to take the Wronskian at this point. So I'm going to do the determinant of e to the t, te to the t, and then the derivative of each of those. So e to the t, product rule would be e to the t plus te to the t. And I know that this determinant would be, let's multiply, that'd be e to the 2t plus te to the 2t. That would be me multiplying these first two together, that diagonal together. And then I'm going to subtract from that the other diagonal, which would be te to the 2t, which simplifies to be e to the 2t, and I know e to the 2t can never be 0, so e to the 2t is the part that I actually want. So my diagonal here that I, subtracted is that one. And then this part right here, this component, this e to the 2t, is this Wronskian piece that I'm going to put into my integral work. So my third step now is to identify all the pieces that I have, or that I'm working with. So let's go through what we've got. We've got our y1, which would be e to the t. We had that over here. We have our y2, which would be te to the t, also here, that we got from our complementary solution. We have now that our Wronskian is e to the 2t. And then the g of t function that I'm working with is that non-homogeneous part. So it would be e to the 2t. Sorry, it does not say that. It says e to the t, t squared plus 1. And that comes from this g of t that the function equals. So there are all my pieces for me to fill in this particular solution. I'm probably not going to write that every time. I just wanted you to see what it was, so you could see our particular solution. So now my job is to find this particular solution, and it says we're going to take the opposite of y sub 1 multiplied by the integral of y sub 2, so te to the t, times the g of t, so that would be times e to the t over t squared plus 1, and I'm going to divide all of that by that Wronskian, which would be e to the 2t. I probably could have written this cleaner. And then I'm going to take and add, that's with respect to t that we're integrating. I'm going to take and add that to te to the t, which is y sub 2, times the integral of, and we're going to repeat that process. So y sub 1 would be e to the t, g of t is e to the t over t squared plus 1 over e to the 2t. And you can see, hopefully you can see, that in each of these integrals, while they look messy to begin with, if we just use a little bit of algebra, it will clean it up quite a bit. So let's do that. So this would be negative e to the t. Up top here, we would have te to the 2t over e to the 2t times t squared plus 1, plus, this would be te to the t times the integral of e to the 2t over e to the 2t times t squared plus 1. And you can see some nice things starting to cancel here. So this e to the 2t will cancel in both of those cases. And now I just need to do my integral work. For this first integral, I'm going to let u be t squared plus 1. So du would be 2t dt which means 1/2 du equals t dt. So really we've got 1/2 the integral of 1 over u du, so this will be the natural log, or 1/2 of the natural log of the absolute value of u plus c. So this first piece would be negative e to the t times 1/2 natural log of the absolute value of t squared plus 1. And then the second part of this integral, I just have 1 over t squared plus 1, 1 over t squared plus 1, which is the arctangent. So this would be t e to the t arctan of t. And this is my particular solution to this. So if we were to write a general solution for this whole differential equation, my general solution would be the complementary solution. So c1 e to the t plus c2 t e to the t. And then we would add in this component here, which was this negative, let's see if I can fit this in here, oops, not sure what just happened there, negative e to the t over 2 natural log of t squared plus 1. I don't really need the absolute value because t squared plus 1 will always be positive, plus t e to the t arctan, oops, not sure what I'm writing, arctan of t. And there's my general solution. So that is how we use the variation of parameters. If you would like to give the next example a go, it's got some fun integration work. And one step that needs to be remembered at the beginning, at the outset of that problem. If you want to try example 2, great. And then you can come back and check your work. All right, here we go. The first thing that you probably should have remembered about this one is that the leading coefficient is not 1, and it needs to be 1. So the first thing I'm actually going to do on this is rewrite this differential equation. Just dividing everything by 2, we'd get y double prime plus 9y equals 3 times the tangent of 3t. And that's actually the function that I'm going to be working with. So first step, I'm going to find my complementary solution. And that is going to come when I do r squared plus 9y. Oops, sorry. I'm not sure what I'm doing. R squared plus 9 equals 0, which means that r will be plus or minus 3i when I subtract that 9 over. So my complementary solution is not super pretty, but I've got my C1. My alpha here is 0, so I don't have to worry about the alpha. I don't have an e to the alpha t. It would be this, e to the 0t cosine 3t plus C2 e to the 0t sine 3t. But I don't have to worry about that, so we're just going to put our complementary to be C1 cosine 3t plus C2 sine 3t. Okay, so now I'm going to deal with my Wronskian. And I have the Wronskian of cosine of 3t. The matrix I'm building is cosine of 3t, sine of 3t. And then the derivative of cosine is negative 3 sine 3t with that chain. And this one would be 3 cosine 3t. That was really meant to be a parenthesis. And we'll do the work here. And I would end up with, let's see, 3 cosine squared of 3t plus 3 sine squared of 3t, which means this result is 3, and of course 3 is not 0, so we're good there. So my y1 is cosine of 3t, my y2 is sine of 3t, my Wronskian is 3, and my g of t is 3 times the tangent of 3t. So let's build our particular solution. So we would have negative cosine of 3t times the integral. Sorry, I lost my train of thought. My y sub 2 is the sine of 3t multiplied by the g of t, which is 3 tangent 3t, divided by the Wronskian, which is 3, plus y sub 2 is sine of 3t times the integral of cosine of 3t. Did not write small enough, sorry. Cosine of 3t times 3 tangent 3t over 3 dt. So let's clean this up a little bit because I've got to try to find a way to integrate this. So we've got negative cosine of 3t. This one, I see the integral here. I'm going to take a little bit of a leap because I know I don't know the integral of sine times tangent. And I could certainly do integration by parts, but that would lead to a loop. Actually, I think I am going to do integration by parts, or we could use trig identities. Let's look at this one. Yikes. Okay, so this integral is going to be fun, actually. I'm going to show you two ways that we can integrate this particular one. We'll come back to it. I'm not going to clean it up too much, so we're just going to leave that one. Plus sine of 3t times the integral here. If we rewrite tangent, I think this is what I was thinking or hoping that this one would do. If we rewrite tangent as the sine over the cosine, then when I multiply this, the cosine of 3t is going to cancel out. So really I'm just left with 3 over 3. That cancels out as well. So this result is really just the integral of the sine of 3t. A much prettier integration piece right there. I mean, yes, I've got a chain rule in there, but we can deal with that. So let's pull to the side and let's look at this first integral. Okay, I'm coming all the way over here. So we're going to show you first, if we were dealing with the integral of the sine of 3t times the tangent of 3t. Those 3's cancel out, so those go away, but the coefficients. Okay, if we did an integration by parts, I would probably let u be the tangent of 3t because I know the derivative of u and I know the antiderivative of sine of 3t. The antiderivative of tangent's a bit messier, maybe. So I'm going to redo this one. So we've got du. The derivative of this would be 3 times the secant squared of 3t dt. The antiderivative of sine would be negative, let's see, with that chain, negative 1/3 cosine of 3t. And integration by parts would say this, u times v. So we've got tangent u v, probably could have written that out front, minus the integral of v du. I am going to throw that 1/3 or the negative out. The 1/3 and the 3 will cancel out. So v du would be the cosine of 3t times the secant squared of 3t dt. All right. Well, if we know anything about secant, hopefully we know something about secant. Secant is 1 over the cosine. So really this expression could be rewritten as 1 over cosine squared of 3t. That's helpful because then we've got, I'm going to pull this 1/3 out front, negative 1/3 times the tangent of, oops, I wrote tangent twice. Negative 1/3 times the tangent of 3t cosine 3t plus the integral. This now becomes the integral of 1 over the cosine of 3t dt. Now, it might actually benefit you to think about this in terms of the secant. We actually had a rule for the integral of the secant. It's a fairly obscure rule. Probably haven't seen it in a while. But let's go ahead. I'm going to clean up this first part as well. But if we take the integral of the secant of t, this integral with that chain rule that's in there would be plus 1/3 times the natural log of the absolute value of secant of 3t plus tangent of 3t. Now, I won't expect you to do one like that on the test, but I am going to clean up this portion too, because we know tangent is sine over cosine, and if I have sine over cosine times cosine, then this really just cleans up to be negative 1/3 times the sine of 3t. So that integral looks like that. Well, that's a lot of work. And there actually is a different way we could have done this same integral. It does require the use of trig identities, or being able to manipulate things with trig identities. And so it looks something like this. I'm going to take that same integral, only this time I'm going to rewrite it. Instead of sine 3t tangent 3t, I'm going to write the original function as the sine squared of 3t over the cosine of 3t. And doing that, I'm going to use a trig identity. So I'm going to rewrite this integral to be 1 minus the cosine squared of 3t over the cosine of 3t. And then I'm going to separate this integral. So this would be 1 over the cosine of 3t minus the integral of cosine of 3t dt. And again, this would require us to know that same rule that we just looked at, which with the u substitution, or the chain rule, basically undoing that 3t, this would be 1/3 times the natural log of the absolute value of secant of 3t plus tangent of 3t minus, and then the antiderivative of the cosine of 3t would be 1/3 sine 3t. So we get the same result either way. Really, it just requires you to know trig identities or some crazy integration rules in both cases. So let's see if I can't move this all back over. Okay, so we get that this integral that we had here, which we could have rewritten as, oops, let's go back to black, sine squared of 3t over cosine of 3t. However we wanted to do this, the end result is this. It's negative cosine of 3t multiplied by that whole function of negative 1/3 sine of 3t plus the natural log of the absolute value of secant of 3t plus tangent of 3t. I think I lost a third in that one. Yep, shoot. This should have a 1/3 in front of it. We're going to go ahead and add that there. Okay, plus then the integral of this next one, I would have the sine of 3t times, that would end up being negative 1/3 cosine of 3t. There's my integration. Let's clean this up just a little bit. I can see several things that are happening here. When I do the distributive property here, when I distribute this negative cosine 3t times this negative 1/3 sine 3t, I end up with positive cosine 3t times sine 3t divided by 3. And then over here, I also have in this case would be negative. This doesn't much look negative anymore, but there was a space between those two. And so this is a negative 1/3 sine 3t cosine 3t. So this ends up canceling out. So we've got one good thing that happened there. So then this particular solution really is just taking this negative cosine of 3t divided by 3 times the natural log of the absolute value of the secant of 3t plus the tangent of 3t. And that is that particular solution. We did all that work, and that is only the particular solution, so I would need to then add it to my complementary solution to make the general solution. So the particular solution would be this solution added to my complementary solution that we had up here. So other than the crazy integration work, how'd you do? All right, there's one more example. This one works out a lot cleaner, a lot nicer. Try example 3 and see what you can come up with. Oh, actually, I didn't realize this one was a little bit different. It's a little bit different because they gave us our first two solutions. So they gave us our y1 and y2, thus they gave us what our complementary solution is going to be. So if we define this complementary solution, my complementary solution will be some constant times the first solution plus some constant times the second solution. And this is what I'm working with here. Now, in order to actually use this differential equation, the first thing that I need to do is solve this. I can't have it equal, my leading coefficient needs to be 1. So I'm just going to rewrite this. Rewriting this, dividing everything by t, we would get y double prime minus t plus 1 over t y prime plus 1 over t y equals just t, because t squared divided by t is just t. Okay, so now I'm going to go through and find my Wronskian. That is going to be the determinant of e to the t times, and t plus 1 over e to the t1. So there's my matrix. Doing the math for this, we would get e to the t minus te to the t minus e to the t, if we distribute that negative through, which means that we get negative te to the t. This can't be 0 as long as t is not 0. So using that as my Wronskian, now I'm going to set up for my particular solution. So y sub p equals negative e to the t times the integral of t plus 1 times t over negative te to the t dt plus t plus 1 times the integral of e to the t times t over negative te to the t dt. So let's clean up this integral work. So we would have my particular solution is negative e to the t, and I'm going to be taking the integral of, well, the t's cancel out. Actually, I could just cancel out the negatives. I'm going to go ahead and make that positive. So we would have t plus 1 over e to the t. And then I'm going to do the same thing here, clean up what I can. E to the t cancels, lovely. We get negative 1 dt. That's the best integral we've had all day. So I'm going to come to the side to deal with this other integral. Do you like how I'm throwing in all of your integration practice? I think this one will be an integration by parts as well. Can't use a u substitution, won't clean up very well. So let's let u be t plus 1, then du would be 1 dt, and dv will let be e to the negative t, because it's in the denominator, so then v would be negative e to the negative t. So uv, I've got a negative in there, so uv times the integral, or minus the integral of v du. I'm going to put a plus there, so we'd get e to the negative t dt. This leaves me with negative t plus 1 times e to the negative t minus e to the negative t plus c. I'm just going to use this portion here. So let's go back into my integration work. Let's come back over here. So my particular solution would be e to the t times that integral, which we just got to be, whether we distribute that e to the negative t in might actually help. Maybe not. Let's leave it t plus 1 e to the negative t minus e to the negative t plus t plus 1 times this integral, which would be negative t. I'm just going to throw this negative out front. Distributing my e to the t in using powers, I would end up with, when I have e to the t and e to the negative t, it'd be e to the 0, which goes away. So we just end up with t plus 1 minus 1. Actually, it looks like I lost a negative. Yep, shoot. Okay, going back here, this should have been a negative t, so this will be a negative t, and this one will be a minus 1. Let's change that. There we go. And then this integral here, we've got negative t squared minus t. Simplifying for my particular solution, we end up with negative t squared minus 2t minus 2. And then my general form would be the complementary solution, c1 e to the t plus c2 times t plus 1, given to me, minus, or plus the function t squared minus 2t minus 2. So that's the variation of parameters. So good luck on your homework, and we'll see you soon.